So in the last video, we introduced this notion called positive definite function. So it basically requires your function to map a certain matrix into a positive definite matrix. And then we also require them to be continuous. And in fact, if you follow Folan's book, Folan is using some slightly different notion. So Folan starts with something he called a positive type, and then eventually he proved that the positive type corresponds to positive definite continuous functions. All right, so I'm just going to show that they're essentially the same definition. And so whenever you read Folan, if he says something is positive type, then essentially it's the same as a positive definite function. All right, but before we do that, I actually want to motivate slightly more what's the kind of the idea behind these positive definite function and why it's defined in the way you see in Folan's book. All right, so here's a little bit of motivation. So it's not a perfect kind of example, but kind of give you the idea of why we look for some condition like you have in Folan book. In other words, what we're going to see very soon. All right, so if you recall the representation theorem, so if I have a phi inside the dual group, inside the dual space of the C0 of G, okay, then representation tells you there's a random measure so that your phi of a function is given by the integral against this measure. And in particular, if your phi is positive, okay, so if phi is positive in the sense that for every f which is positive, then your phi f is also positive. So if you feed in some non-negative C0 function, then if your function always returns something that's also non-negative, then the measure itself has to be non-negative, okay? So you don't have a sign measure, but you always have a positive measure, okay? So that's kind of the idea. So this kind of idea is that the positivity of the functional, okay, so the positivity of some functional is kind of corresponds to the positivity of on positive elements, okay, so it looks like the positive value on some positive element, all right. So that's kind of the idea. The positivity, so the measure mu, you treat mu as a measure, but also you can treat it as a functional. So the positivity of this measure or this functional is essentially the same as saying the mu when you evaluate on some positive elements. In the case of C0 is basically all the positive functions. Those are the positive thing in the C0s. Okay, so as long as you have positive value of there, your functional is positive, okay? So that's kind of the idea. Well, now what happens to your positive definite function on groups, okay? What is it? So now we have this P of G, we saw that is actually, we can realize that as a subset of the L infinity of G, and L infinity, you know, that's the dual space of the L1 space. So this you can realize the P of G as in the dual of the L1 space, okay? So in other words, well, what is the positive element in the L1, okay? So in other words, what is positive in, well, let's just use quotation because this is highly non-rigorous. Okay, so the idea is what kind of thing is positive in the L1 of G. Okay, so, well, what is positive? Well, this is a very difficult question. So if you, well, you may tempt to say, well, the positivity means things when your function is positive. Okay, your function is positive almost everywhere. Well, if you do that, well, of course, you can treat the L infinity of G being the dual space. Well, you can show that your L infinity basically has to be, if you want to map those positive to positive, then your L infinity has to be positive. Of course, also in the pointwise sense. But you see, this is not the same as the positivity we defined on these positive definite functions. We define it as certain matrix being positive. So this is slightly more trickier than just pointwise positivity on the L1 of G. Well, another way of looking in this L1 of G again is we treat it as a Banach star algebra. So it has a convolution and an involution. And if you study some operator theory, especially if you move on to, say, positive operator or some C-star algebra, there's a concept of positive elements that looks like, so the positive elements in the star algebra, usually they looks like these A convolute with is involution, okay? So these kind of things are kind of the positive elements, okay? And now we're essentially just going to show that positive definite is essentially just map these positive elements to positive value, okay? So that's all I need to show in this video. So here is the big proposition. So I want to show that the following are actually equivalent. All right, so the first is being this phi is positive definite, so it's positive on a bunch of matrices and continuous. And second, what in fact this means is that if I treat phi as an L infinity function, so I can test against some L1 function, then against those positive like function, which is A conjugate, A convolute with the involution of A. So let's say for every f in the L1 of G, okay, I consider f convolute with f check, okay, so that looks like those positive things. And if I treat my phi as an L infinity function, so I can consider it is functional. So let's just do the usual left hard measure. Okay, so this is going to be non-negative, okay? You see, this is essentially saying phi as a positive linear, as a linear function on the L1 space, map those f times f check to positive values, okay? So that's kind of the idea. All right, and in fact, I don't need the L1. I can just use the compactly supported. So for every f in the CC of G, the integral of the same thing, okay? So still involution of dx that's non-negative, okay? These two are kind of trivial. CC of G is going to be dense in the L1, so of course CC of G is also containing L1, so these two are clearly equivalent. And also I can write this integral slightly more clear. So this probably you'll see it as a continuous version of our positive definite condition, all right? So for every f in the CC of G, okay, of course you can just require to be in the L1 of G. They're essentially the same thing. You do the double integral of your, if you evaluate your function at x and you multiply function value at y and you conjugate, and you multiply something like a kernel each thing, phi of xy inverse, okay? This one is going to be greater than or equal to 0, okay? So this is really just a continuous version of your positive definite matrix, okay? Your positive definite matrix is essentially, if you think about, you evaluate your matrix at a few points, and then you do the double summation, okay? Now I'm doing a double integral, okay? But the idea is really the same, okay? So I should just say this is a continuous version of the positive definite condition, okay? All right, so it turns out they're also equivalent. And finally, I want to say not only that, okay, if you treat your function as a dual of the measure space, you also have something similar. So for every lambda inside your measure space, and you integrate your phi against the convolution of the measure against its involution, of course, okay, then you have something that's non-negative. Okay, so it turns out all these five are equivalent. All right, so now let's give a proof. All right, so let's do some easier part. So first of all, 2 and 3 has to be equivalent. I already mentioned it because the CC of G is first of all containing the L1 of G and it's going to be dense. So you approximate all the L1 by CC of G and the other direction is trivial. Okay, so 2 and 3 has to be equivalent. 2 and 3, they're both equivalent to 4. So 2 and 3, they're really just equivalent to 4. Well, the reason is quite simple because 4 is essentially just rewriting this double integral. All right, so if I consider this double integral, so let me write the single integral first. So I integrate the convolution, okay, this positive element, okay, and then I have phi x dx. All right, so I can use the definition of the convolution. Now it becomes a double integral. I have f of xy inverse, f check of y, and then I have this phi x dx, okay? And well, because my this group again is abelian, so I can just really use another formula. So when because my modular function is equals to 1, another way of writing this convolution is that I move the inverse to the other side. Usually I need to pay a price of the modular function. Well, let's just move it there because I have modular function equals to 1. All right, and now I have, by definition, my f check is essentially just the f of y inverse, the whole thing inverse again, and then I take the conjugate. So this expanded, that's equals to f of xy, f of y, the whole thing conjugate. I have a phi x, I should say dy here, so dx dy. And let's change the integral. So let's move the fy conjugate outside. I integrate the fxy phi x dx dy, and then I use the translation invariance. So I want to have an f of x instead of f of xy. So for this fixed y, I can translate to the other side. So this becomes the integral of fy bar. I have the integral of xy now becomes x, so x becomes xy inverse. And then I have a dx dy, okay? And then you just move the fy bar inside, you get 4, okay? And essentially, because these are equivalent, so number 4 is equivalent to 2 and 3, okay? That's also kind of trivial. All right, so now I basically need to show that number 1 being positive definite is equivalent to 4 and equivalent to 5, okay? So now let's do the cycle thing, okay? So let's do 1 implies 4, that's the easier one. All right, so for every x1 up to xn inside G, so because it's positive definite, so I have the phi of xi, xj inverse, that's a positive definite matrix. In other words, if I take any C1 up to Cn inside the complex, then we have this double summation, so over I and j from 1 to n, Ci, Cj bar of phi of xi, xj inverse, okay, that's going to be greater than or equal to 0. Sometimes I write xi inverse xj, sometimes I write xi xj inverse. Things are abelian, doesn't really matter, all right? And because this is greater than or equal to 0, so now what we can do is the following. So I want to prove 4. In other words, I want to show that for every compactly supported function, this integral, okay, over here, that's going to be non-negative. Well, so let's say for every f inside the CC of G, and if you think about this function fx times the fy conjugate, okay, so that's actually inside CC of G cross G as well, okay? So because all your function can be approximated by some simple function, so let's say some psi n, which is equals to some, let's say C ni chi of eni, okay? So here I come from some index mn, right? So that's going to converge to your function f, okay? So that's in the basically a uniform convergence. All right, so because here I have this convergence because the function is compactly supported. So what I can do is I approximate this fx fy bar by the psi n and the psi n bar, okay? So this double integral of the fx fy bar of phi of xy inverse dx dy, that's going to be the limit as n goes to infinity. I get better and better approximation of the double integral of the psi nx psi n y bar of the phi of xy inverse dx dy. And because psi n are simple functions, you take a product of them, they're still simple. This is fairly easy to evaluate. So for each fixed n, you can expand it as a double summation now, okay? So you have a CNI, CNJ bar, and then you multiply the measure of, say, ENI and the measure of ENJ, and then you have the phi of the XNI, XNJ inverse. Okay, but in any case, this is going to be positive. So this is positive. So you take the limit. Again, it's going to be positive. So this finished the proof that 1 implies 4. Well, to show that 5 implies 1, okay, so let's say 5 implies 1. So suppose you have your integral, because the integrate against all the convolution of 2 measures, they're always positive. You can actually just pick a particular one. Let's take a bunch of point mass. So a bunch of summation of the Ci delta Xi. Okay, so this is certainly inside your M of G. Well, we talk about when we what is the convolution of this Dirac measure, basically pointwise measure. So recall, if you have the delta X, if you do the check, that's essentially just the point mass at X inverse. And if you convolute 2 point mass, delta X and delta Y, that's just the delta XY. So because of that, this integral against this measure is going to be really simple to write. Okay, so this is essentially going to be the double summation of the Ci Cj bar of phi evaluate against the delta of Xi Xj inverse, which is essentially pointwise evaluation at Xi Xj inverse. Okay, so let's do Xi Xj inverse. And that's, we know, is positive by the condition 5. All right, so that finished the proof that this is non-negative.